welcome to Grade 12 Data Management, Lesson 4.5, Hypergeometric Probability Distributions. Today you're going to learn how to recognize conditions that give rise to hypergeometric distributions, calculate the probability associated with each random variable of a hypergeometric distribution, represent it using a table and a probability histogram, and solve problems. So a hypergeometric probability distribution is a distribution with dependent trials whose outcomes are either success or failure. So this differs from the geometric distribution we discussed last lesson, in that it is dependent trials, not independent. The random variable is the number of successes in a given number of trials, and the probability of X successes in R dependent trials is given by this beautiful formula, which looks a little crazy, but we'll break it down and you'll see how easy it is. Where A is a number of successful outcomes available within a population of size n. You've actually probably already seen this before and you'll recognize it. So let's just jump straight into an example and demystify hypergeometric distributions. So a 5-card hand is dealt from a standard deck of cards. That means, all right, 5-card hand, that means my R, which is my trial, my 5-card hand is R, and standard deck of cards, we've got n equals 52. Okay. Calculate the probability distribution for the number of hearts in the hand. All right, so we've done questions just like this before, number of hearts in the hand. Let's think about it. When we're talking up here about probability of X successes in R, right? Probability of the number of hearts in R, which is 5-card hand, where A is the number of successful outcomes available within a population of size n. So the number of successful outcomes available to us in this case is the number of hearts available to us, which is 13. And we can determine our random variable to be the number of hearts. So once we've declared what our random variable is, let's start with a table. So we have a random variable x, which can take the values of 0, 1, 2, 3, 4, or 5. Why? Because we're getting a 5-card hand, so you can have either 0 hearts, 1 heart, 2 heart, 3 heart, 4 hearts, or 5 hearts in that hand. And then let's look at the probability of that happening. Now this is nothing new to you. You will recognize this formula. Probability of 0 hearts in one hand. Now watch carefully as I describe this. So 0 hearts means out of those 13 hearts, we are going to choose 0, none of them. And out of the 39 remaining cards, we're going to have 5. So we're going to have 5 cards that aren't hearts. That's what that is saying. Out of a possible 52 cards, choosing 5. You recall that formula, we have seen this before. And that gives us a value of 0.222. Okay, now the formula just repeats, but instead, now for the next one, we're going to have 1 heart. So the change in the formula will be this: 13 choose, now choose a different color so you can see it, 1. And then the next bit stays the same. Out of the 39 remaining cards, we're going to have 4 because we already have our 1 heart there. And the rest of the formula stays the same, 52 choose 5. And obviously that computes a little bit differently, so 0.411, and so on. So let's keep applying this. I'm not going to go in blue now, just for the sake of speed. So 13 choose 2, and 39 choose 3. Out of 52 choose 5. Making sure that the numbers, if they were all blue, would add to 5 every time. So this one is 0.274, and let me just silence my phone there, sorry about that. And then P3 is 13 choose 3, 39 choose 2, divided by 52 choose 5. The denominator stays the same, 0.082. And P4, 13 choose 4, 39 choose 1, divided by 52, choose 5, and that's 0.011. And I'm calculating this so fast because I've done it before in advance, okay? So in case you're wondering. So now we're at the 5 hearts in a 5 card hand. So 13 choose 5, 39 choose 0, which is kind of redundant because that's just 1, but we write it all the same just to help with your understanding. And that's 0.0004. Okay, so now when you add all those together, the sum of the probabilities of the distribution will equal 1. The sum of probabilities, and you can check that as well, is 1. What does P5 tell you? Well, P5 just tells you what it says. What is the probability of getting 5, what is it, hearts? Yes, hearts we're dealing with. 5 hearts in a 5 card hand. From a standard deck, right? So why do I ask this question? Just for your understanding. You need to understand what's happening here, okay? All right, so let's do a probability histogram based on those. So if you are writing this note out, just make sure you have that just bent over so you can see that page there with these probabilities here. We're going to be graphing these probabilities on a probability histogram. So what will that look like? Well, we have, let's label up our histograms first down at the bottom. 1, 2, 3, 4, and 5. This will be the number of hearts in a hand, and this will be the probability of that happening. So we go up to 0.411 as a maximum. So let's do this 0.10, 0.20, 0.30, 0.40. You might find it easier to do your probability histogram if you label them up like that with 2 decimal places instead of 1. Okay, so the first one, probability of 0 hearts was 0.222. So 222 is about there. I'm going to do all my horizontal lines first. Then probability of 1 is 0.411, kind of right there. Probability of 2 is 0.274, which will be right about there, I'm thinking. Probability of 3, 0.082. 4 is 0.011. And 5 is down there. Okay, now I'll do my vertical lines. You can use a ruler. I did use a ruler on yesterday's class histogram, and it worked quite well using a ruler on an iPad, but for the sake of speed today, I am just going to freehand it. Okay, I've put dots at the middle on the top of each histogram bar so that I can draw an approximate curve going through those points to demonstrate the shape of this distribution. And you can see that the shape of the distribution is definitely right skewed because of the tail. So right skewed. And that's how we describe it, using the words that I gave you in the previous lesson, few lessons back. Right skewed or left skewed, normal, uniform, or bimodal. Let's calculate the expectation and its meaning. So the expectation or expected value of this, we're going to just take from this table, we're going to take the yellow values that I've highlighted right here and multiply them to the ones that are highlighted in blue each time for each value of x, and then add them together. So that looks like this. So we have 0 times 0.222. 2 plus 1 times 0.411 plus 2 times 0.274 plus 3 times 0.082. Just going to move this out of the way because it's kind of in the way. There we go. And let's go back. All right, plus 4 times 0.011 and plus 5 times, I can't remember the last one, 0.0004, 0.0004. Okay, and that comes out to be 1.25. Okay, all right, what does it mean? It means likely 1.25 is approximately 1, closer to 1 than it is 2. So we would expect to have 1 heart in a 5-card hand. And that is it. Okay, all right. The expectation for a hypergeometric distribution. So let's look at an easy way to do it. So when determining the expected value for a hypergeometric distribution, you can simply multiply the number of trials R by the number of available successes in A and divide it by the size of the population N. So recall that in our previous example, we have number of trials R, which is we're pulling 5 cards, we're multiplying that by 13 possible hearts, and we're dividing by 52. And when you put that into your calculator, hopefully you get 1.25, I think. Yes, indeed. 13 divided by 52, 1.25, which is what the answer we got above. Okay, so in a class of 23 students, 14 have their driver's license, 8 students are selected at random. So how would you know to use this hypergeometric distribution or to use the geometric distribution? Well, in this one, 8 students are selected. That's selecting without replacement, which means it's dependent. Let's just formalize that. So selecting without replacement means dependent. And hypergeometric distributions are based on dependent events. What is the probability that at least 3 of them have their driver's license? Okay, so now we have number of students is 23. We have our number of successes, I guess, the number of people who we could select from who do have their driver's license is 14, and we are selecting 8 students. So, probability of at least 3, so our random variable has got to be greater than or equal to 3, which means 1 minus probability of 0 driving licenses, 1 driving license, or 2 driving licenses. We could do it the direct way and do the probability of 3 plus 4 plus 5 plus 6 plus 7 plus 8, but that's just a little bit longer to calculate. So off to the side, we can probably actually do it right here and there. Probably have enough room. So this will be 1 minus probability of 0. That means we're going to, out of 14 people with driving licenses, we're choosing 0 of them. And out of the remaining 9 students, we're going to choose 8. And that would be out of a potential 23 students choosing 8, just at random. So that's the probability of 0 students chosen that have driving license. Okay, next one, probability of 1. So that's 14, choose 1. And out of the remaining 9 who don't have licenses, we've chosen 7. Out of 23, choose 8. And you'll see that the denominator is the same as the previous one again. So the only thing that is changing are the numbers that I'm now going to highlight in blue and this one. So the next one, 2. We've got 14, choose 2. And then we have 9 students, and we're choosing 18 total, so that means we've got 6 going on there. And 23 choose 8. Okay, so that is P2 right there. So when you put that into your calculator, hopefully you get something like 0.983. Try and feel confident and put that into your calculator all at one go, or you can break it down, just write in each individual step, but try not to round too much at all at this point. If you're going to leave your answers to 3 decimal places, then don't round to anything more than 4 decimal places when you're doing the interim calculations, okay? All right, what is the expected number of people that have their driver's license? Well, the expected number of people, we can just use that lovely handy-dandy formula of RA over N, recalling that these are our values right here, which will just simply be 23 times 14. Nope, that's not right. Whoops, back up, Mrs. H. Or 8 times 14 divided by 23. And that should give you 4.9 approximately. All right, so how do we translate that? Let's look at the context. We're choosing people at random. So we would expect not 4.9 people, but we would expect to have 5 people out of 8 chosen to have their license. Okay. All right. So let's look at another example. And this one will be right there. The Ministry of Wildlife came to Uxbridge and caught 120 red squirrels and fed them green food colouring until their fur turned green. Then they were set free. A month later, the ministry came back and caught 15 squirrels, of which 4 of them were green. What is the approximate size of the squirrel population in Uxbridge? This is a delightful question. All right, so with here we've got to think about what we can assign to the values N, A, and R. Okay, so our N, which is our population size, we don't know. That's what we're being asked to find out. My A. So the A is the successors. So we're looking for green fur, and they caught 120 red squirrels. So we know there's a population of 120 red squirrels that turned green in the environment, right? And when they actually caught them, 4 of them were green. But what did they catch? They caught 15 squirrels, okay? And we can say that our expected number of squirrels caught when you catch 15 squirrels was 4. That's what's given to us right here. That's the value that we have there. So let's work backwards. We know that the expected value is going to be R times A divided by N. So therefore, we can confidently state that 4 equals R, which is 15, times A, which is 120, divided by N, which we don't know. And now it's just a simple case of solving for N. So we can cross multiply. So N equals 15 times 120 divided by 4. And then if you want to slash and burn and do a little bit of division, then you can do. And then you can solve it that way, or just put it straight into your calculator. I don't mind. 15 times 3 is 445, so 450, I believe that is. Check that on your calculator just in case. All right, so we can therefore say there are approximately, and we're talking about squirrel population here, red ones and green ones, there are approximately 450 squirrels. Okay, and that is it. You have homework that is associated with this, and also those extra practice questions if you wish. And happy Friday. Have a wonderful weekend, and I will see you next lesson. Take care. Bye-bye.